physics class. In the previous video, we have done about electric potential at any arbitrary point due to an electric dipole. From there, with a special case, we can find out electric potential due to an electric dipole along its axial line or along its any equatorial line. Got it? And for today, we will try to find out electric potential energy of a system of charges. So what is this potential energy of a system of charges? Let's try to define that first, and then we will try to do these special cases, or for separately for 2-point charges. I mean potential energy of a system of 2-point charges or 3 charges or multiple charges. Okay, so let's try to define this electric potential first, and then it will be I mean electric potential energy, not electric potential. You know, electric potential and potential energy are different. Okay, this is the work done. When I say electric potential, it is nothing but it is only the work done per unit charge. When I say electric potential energy, it is nothing but it is the what? Potential energy means what? Work done per unit charge, right? So what is this electric potential energy of a system of charges? So electric potential energy of a system of point charges is defined as the work done in bringing these charges in their respective locations from infinity to form the system. Okay, suppose if there are many charges here, and these many charges, if you want to find out their electric potential energy, then it is defined as the amount of work done in bringing these charges from infinity up to their respective positions. Okay, from infinity to form such a distribution of charges here. Got it? That is known as electric potential energy of a system of charges. Let me repeat. Electric potential energy of system of charges is defined as the work done in bringing these charges in their respective locations from infinity to form the system of charges. Got it? Yes. Now let's try to find potential energy of a system of 2-point charges. Here there are only 2-point charges. So these 2-point charges, as there are no other charges in its surrounding, then we will call it this as a system of 2-point charges. Got it? So let's try to find for 2-point charges, then 3 charges, 3-point charges, and then we will generalize it for what? Multiple distribution of charges. Got it? So now these two, Q1 and Q2, these are the 2-point charges. We have to take it that these 2-point charges were at infinity. Okay, were at infinity. Now let's try to bring these Q1 and Q2 one by one at their location. Okay, now when these Q1 and Q2 were at infinity, let's try to bring only Q1 from infinity up to this position A, of whose position vector is denoted by R1. Got it? So when Q1 from infinity, it is brought from infinity to this position at A of position vector R1, there is no work done. Why? Because when we bring this Q1 from infinity, there were no field around this position A. There is no field or no external field, so there will not be no work done in bringing this Q1 from infinity up to this position, okay, at A. Got it? So there will not be no work done. But when you try to bring this Q2 from infinity up to this position at B, there will be electric field due to this Q1. So due to this Q1 there will be electric field, and against that electrostatic force of this Q1 you need to bring this Q2 from infinity up to here. So naturally there will be work done, right? So work done in bringing, in that case what happened, work done in bringing Q2 from infinity up to this point, okay, inside the field due to this Q1. Got it? That work done will be known as what? Potential energy of a system of 2-point charges, right? So first let's try to write that one. If you want to write the note, then you can copy down this, right? So therefore, as I said, whatever I have said, it will be all here, okay? So work done will be equal to what? Potential into Q2. What is this potential? V. This is the electric potential of what? Of Q1 at B. Okay, this is the electric potential due to a single point charge. You take it in that way. The potential at B due to Q1 is denoted by V. Got it? So where capital V is the electric potential of Q1 at this point B. So what happened when you want to find what potential? Then what happened? Work done divided by the charge. That means work done per unit charge. We call it as electric potential. So from that definition, work done will be equal to what? B into potential into Q2. So your work done will be equal to electric potential for this Q1 at B. Okay, that will be equal to what? 1 by 4 pi epsilon naught Q1 by AB. And I missed one thing here. This will be Q1 times of Q2. So Q2 is missing here. So you need to put Q2 here. Got it? This portion is for what? This portion is for electric potential of Q1, okay, at the point B of distance how much? Far? AB. And AB, if you want to try to express this AB in terms of the position vector R2 for the point B, and for the point A the position vector is R1 vector. So if you want to express in terms of these two position vector R2 and R1, your AB will be equal to what? R2 minus of R1 vector. Can you see? Let me zoom in, okay, like this. So what happened? This is just like the triangle law of vector addition, whatever you have learned in your class 11. So this is one vector, another vector, this is also another vector AB. So R1 vector plus AB vector will be equal to R2 vector. This is your triangle law of vector addition. Okay, so your R1 plus AB vector will be equal to OB vector or R2 vector. That means your OA, let me write, I can't write it, okay. So you just listen me. So the first vector is what? R1 vector. The second vector is what? This AB vector from A to B, and it will be equal to the third side of a triangle taken in the opposite order. That means R2 vector. Okay, R2 vector will be equal to R1 vector plus AB vector. So your AB vector will be equal to what? R2 vector minus R1 vector. But for us here, we are going to take not the vector quantity, rather we are going to take only the distance. Okay, so for taking distance, you have to take modulus. Got it? R2 minus R1 vector is nothing but AB vector. We want to take only the distance, not the direction from here A to B or B to A, doesn't matter. You have to take only the distance. So it will be modulus of that of R2 vector minus R1 vector. This work done is stored as a potential energy U of the system of charges. So in these 2-point charges, a system of 2-point charges inside it, that potential energy will be stored, or that work done will be stored in the form of potential energy, and that potential energy can be expressed as what? 1 by 4 pi epsilon naught q1 q2 by R12. R12 is nothing but the distance from here to here or from here to here. That distance R12, that means in distance between 1 and 2, q1 and q2, that is the meaning. Got it? Yes. Next let's try to see potential energy of 3-point charges. So let's try to increase from 2 to 3, and then we can generalize it for nth point charges. Okay, system of nth point charges. Got it? Yes, this is a potential energy of 3-point charges. Like that, in the case of 2-point charges, we brought first q1 and there will not be no work done. Okay, likewise here also we have to assume all these 3 charges q1, q2, q3 were at infinity, and you need to bring one by one q1, q2, q3 at their respective positions. Got it? And the amount of work done in bringing these 3-point charges in their respective positions from infinity, that amount of work done will be known as what? Potential energy of a system of 3-point charges, right? So let's take it that these 3-point charges were at infinity, and let's try to bring q1, q2 separately. Now let me tell you first, and then we will see those formulae later on. Okay, how to find it out, that one we will take it later on, but first listen me first. You need to have that concept first, and then the formula or the derivation will be very easy. Okay, so when these q1 and q2, q3, they were at infinity, at first when you bring q1 at this position A, at the point A from infinity, A is having position vector r1. So what happened? There will not be no work done in bringing q1 from infinity up to this location A. Why? As I said in the previous 2-point charges, there will not be no external field, and as there is no external field, this q1 was brought against any electric field, so no work done. Okay, so what happened in bringing this q1 up to this position A? No work done. But when you bring q2, okay, when you bring this q2 from infinity up to this position, then this point is under the influence of this q1. That means electric field will be surely there due to what? Due to this q1, and so electric potential for this q1 at this point will be there. So what happened? The amount of work done in bringing this q2 from infinity up to here will be equal to what? V times of what? q2. What is that V? We can call it as V1. That V1 is nothing but the electric potential of this q1 at this position. Got it? So there will be what? Electric potential energy when we bring q2 from infinity up to this point. Up to that part, that will be just like potential energy of a system of 2-point charges, right? But now when you try to bring another 3rd-point charge from infinity up to this point, then what happened? There will be two different work. Why? Because we have to bring this q3 against 2 electrostatic force. One electrostatic force is due to q1, another electrostatic force is due to this q1. So you need to do 2 additional work when you bring this Q3. Got it? So what happen if you take it that V2 and V1 are the potential at this point C due to Q1 and Q2 respectively, then what happen? What I said, if V1, if you take it this as V, okay, at potential due to Q1, if you take it that as V, let's take it as V, okay, V1 is what? Electric potential due to Q1 at C. Got it? So let me write it 1C like that so as to make you understand. Okay, this is what? Electric potential due to Q1 at the position C. Another, let's take it as electric potential due to Q2, got it, at C. Okay, so there are two potential at this point C. So against that potential, or rather against that field due to this Q1 and Q2, what happened? You need to bring this Q3. So your total work done in bringing Q3 from infinity up to this position C, your total work done W will be equal to what? V1C times what? Your Q3 here plus V2C times of what? Q3. Got it? So this is the amount of work done in bringing what? That Q3 from infinity against the charge, against the electrostatic charge due to this Q1, and the second term is against the charge or against the field due to the charge 2. So this is a total work done. Got it? So let's see. Consider a system of 3-point charges Q1, Q2 and Q3 such that Q1 and Q2 are initially at infinite distance. Even you can take it Q3 also at infinite distance, as I have said in the case of 2-point charges. And if you try to bring that Q1 from infinity up to this point, no work done. Okay, you can write it in that way also, no doubt. If you want, you can write whatever the writing here in the slide. Work done to bring charge Q2 at B, at this point B, will be equal to this Q1 by Q2. There 1 by 4 pi epsilon naught will be always there, because the intervening medium between these two charges, we take it as vacuum. Okay, that's why 1 by 4 pi epsilon naught is there. And had there been any medium, then this would have been what? Epsilon. Got it? And that epsilon is nothing but the what? Relative permittivity of that medium, right? Yes, into what? Q1 Q2 divided by R2 vector minus R1 vector. Being this is the modulus, so you can take it as R1 vector minus R2 vector, and then you take it modulus. When I say modulus, then there is no direction. We represent only the distance between what? A and B. That will be given by this R2 vector minus R1 vector, or modulus of R1 vector minus R2 vector. Okay, when if you take modulus, then R1 is writing first or R2 is written first, doesn't matter. Okay, both are same. If you just interchange these two without modulus, then 1 minus sign will be coming up. As you are going to take modulus, then only the magnitude will be taken. Okay. So you try to remember this diagram, and let's try to switch on to that next slide for finding out this work done in bringing what? Q3 from infinity up to this position. Okay, yes. Now when Q3 is brought from infinity to C, okay, of position vector R3, then work done is against the electric field due to what? Q1 and Q2. Okay, so there are two external fields, we can say. When you try to bring Q3 up to that position C, there are two external fields. You can think it in that way. One external field is due to Q1, another external field. Second is due to Q2. Okay, so if you try to bring this, the work done will be denoted by 1, 2, 3. That means when you try to bring this third charge against the field of Q1 and Q2, okay, that will be equal to what? Work done in bringing that charge Q3 inside the field of Q1 plus work done in bringing that charge Q3 inside the external field due to the charge Q2. So that will be equal to what? We can write 1 by 4 pi epsilon naught 1 3. When it is 1 3 is there, 1 3 3 1. Okay, or 1 3 you can write, doesn't matter. Modulus of R3 vector minus R1 vector, like that. Similarly for this also. So your total work done will be equal to what? This here, this one here, and that this W12 was the previous slide. There we have written that this will be equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R2 vector minus R1 vector modulus. Here, this here. Got it? So this is what work done in bringing that Q2 against the electric field of Q1. So that will be equal to this one. Okay, and this is what? Due to this 1 3, okay, against in bringing that Q3 against electric field Q1, in work done in bringing Q3 against the electric field of Q2. When you look very closely, okay, when you look very closely, then what happened? This portion is nothing but this is the electric potential. Okay, this is the electric potential of Q1 at position what? B. That means at the position of that charge Q2. Got it? This is the electric potential of Q1 due to Q1 due to the point charge Q1 at the position of this Q2. Got it? That means at the point B. And this is what? This is the electric potential of Q1 at the position of the charge what? Q3. At the position of charge Q3 means at the position what? C. And this is also just like that, electric potential of the charge Q2 at the position of Q3. That means at the position C. So this is what? B due to what? The second charge at the position C. This one is also what? This is the electric potential of the charge 1. That means Q1 at the position of this Q3. That means at the point C. And this is what? This is electric potential due to the charge what? 1 at the position of Q2. That means at the position B. So V1B times Q2 will give you your potential energy. V1C times of Q3 will give you the potential energy in bringing Q3 against the electric field of Q1, and this will be what? Electric potential energy. That means what? V2C times of Q3. Got it? Yes. Let's see. Now if you this was already there in the previous slide. Okay, just to make connection I'm just giving you this. Otherwise you can skip this portion because you have already written this one. So this will be equal to, when you look all the three terms, okay, you will see 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught. So you take it, this 1 by 4 pi epsilon naught common here, and then within the bracket it will be what? Q1 Q2 divided by modulus of R2 vector minus R1 vector, like that, so on. Got it? So in the form of summation, we can write these as half times of this 1 by 4 pi epsilon naught summation of this double summation, I should say, Qi into Qj, okay, divided by modulus of Rj vector minus Ri vector when I goes from 1 to 3 and j goes from also 1 to 3, where I is not equal to j. What is this meaning? This is the summation. If you want to expand this, then it will come in this manner. Okay, why this one another factor half is coming up? It was not there half. When I take it this, I should be also goes from 1 to 3. J should also go from 1 to 3. And after writing that, what you have to take the sum. So if you are going to take it that in that way, I also goes from 1 to 3, J also goes from 1 to 3, then the term, okay, within this, okay, removing, not including this one, okay, you can write it this term. Forget about this half for the time being. Okay, 1 by 4 pi epsilon naught will be always there, no doubt. If you try to expand this, then it will be coming in this way. I is not equal to J means what? When you take this 1, you cannot take it this as also 1. When you take this 2, this cannot be, J cannot be taken as 2. That means these two should not be same. Okay, that is the meaning of this. I is not equal to J. So what happened? If you started from 1, then this will be 1. Okay, 1 1 we cannot take it, so 1 2, J will be 2, Q1 Q2, Q1 Q3. Got it? Like that. And if you take it I is as equal to 2, then you can take this 2, J can take 1, but J cannot take 2. So that Q2 Q2 I'm not writing here. Got it? Here also I did not write it as Q1 Q2. Why? Because J cannot take the same value as I. Okay, so we will start from Q1 Q2, then Q1 Q3. When I take it also for I equal to 2, then Q2 Q1. Okay, I cannot take it that Q2 Q2 in the next. Got it? So we will not take it, rather I have to take it Q2 Q3. Got it? And here also Q3 Q1, Q3 Q2. Next it will be Q3 Q3. So I can't take it that Q3 3 same due to this restriction, so I did not write it. So when you write like this, what happened? There are what similar terms coming up twice. Q1 Q2, Q2 Q1. This is just changing. This is a product. Q1 times Q2. Here also Q2 times Q1. That is also same. Q2 Q1 times is equal to Q1 Q2. And for this Q1 Q3, another Q3 Q1 is there. So Q2 Q3, Q3 Q2. So these similar terms are coming 2 times. So just to cancel that doubling or coming twice of the similar term, you just divide it by 2. That means half. So that 2 and this coming of 2 times, there are 2 factor 2, 2 will cancel, and you will be getting as it was before. Clear? Yes. That is what this double summation gives you a factor of what? So this factor half is introduced, or it is coming because its term is coming twice. Okay, such term is coming 2 times. That is the meaning. Now after doing this, let's try to find out the potential energy, rather your electric potential energy of a system of nth point charges, okay. So in that nth point charges, we will have to do like this only, this in this form. Only thing we need to replace it, what? This, instead of having only 3, we need to go from I goes from 1 to n, J goes from 1 to n. Got it? And we need to what? Know how that is coming. That one I will tell you here. Okay, yes, this is what potential energy of a system of n point charges. Instead of having 3, we are having here n point charges. Got it? We don't know how many n, how much the value of n is, but we can take it for this n is equal to 3 and equal to 2. You can deduce it from this general form. So consider a system of n point charges q1 q2 so on up to qn, place at position vectors r1 r2 so on up to rn vector respectively. Potential energy of the system of n charges is what? Half factor is there. Why? Because those similar terms are coming two times, right? Because of that, one factor half is introduced. So 1 by 4 pi epsilon naught was there in that previous formula. So double summation will be also there. I goes from 1 to n instead of 3 in that previous formula. Then j will also go from 1 to n, and we should not take it that I is what equal to j. Rather, we have to take it that this I and j are not equal. And then q1, q2, instead of that like that, we will have I, j, q1, q, I, q, j, q, can you see? Summation of qi, qj divided by modulus of rj vector minus ri vector. So this will be equal to half of summation of qi and vi. Okay. Now this, what is this actually? Let's see. Not. Okay, this is a formula for that of, you can write only this much, but what is this? qi and qj. So this from here to here, forgetting about that what q j, this portion is for the electric potential energy. Okay, electric potential I should say, for the electric potential what at their locations, and this is what electric what potential. Got it? Electric potential times the charge, you will get as what? Potential energy. Got it? Yes. So from all these expressions, what we can conclude is that potential energy of 2-point charges in external field, okay, we can find it out that very easily. And next, potential energy from this distribution of charges, what we can obtain is that this q1 v1, this is for 3-point charges. Okay, this q1 potential at the distance r1, if you think of that of what the 3-point charges, then this will be q1 when you try to when you try to bring, I'm sorry, I'm a little bit confused. Now what we are going to find out is that in that previous what we have done, there were no external field. When we try to bring that q1 from infinity up to that position A, no work done, right? Had there been some external electric field at the vicinity of that position A, what happened? There will be surely work done. Okay. So what happened when that 2-point charges, okay, are brought from infinity up to those positions having some external field? Okay, then what happened? The formula will be little bit changed. Why? Because when you bring q1 to that position A, there will be surely work done because external field is there. So against that external electric field, you need to bring q1 from infinity up to that position capital A, right? So in that case, what happened? You need to have the work done for this, for bringing that q1 at a position capital A of position vector r1. So q1 times the potential, rather the electric potential at r1 due to the external field. Got it? Similarly, for this, in bringing q2 also, what happened? There will be what? A work done in bringing what? This q2 from infinity against that external electric field. And another additional thing, in bringing that q2 from infinity, there will be another external work against the electric field due to what? q1. Got it? So what happened? This first one, are you clear with this one? So in bringing Q1, suppose if there are external field like this, okay, let's take it as uniform. Uniform electric field is represented by parallel lines equidistant from one another with an arrowhead represents what? Your uniform electric field. So let's take it that there is an external electric field here like this, and let's take it that this is point A. Think that this external field is all separate, distributed somewhere here. That means here electric field all here in this way parallel. Okay, now B is somewhere here, and let's take it that this is your axis and this is your origin. A has a position vector, let's take it as R1. Okay, R1 vector, and your B has a position vector like this. Let's take it that P is somewhere here, or position vector, say R2 vector. R2 vector in this way. Got it? So this was an external field. When you bring that Q1, okay, from infinity, these are at infinity, okay, Q1 and what Q2 are at infinity. Now from infinity you need to bring this Q1 from infinity up to this position inside the electric field. Okay, so what happened when you try to bring this Q1 from infinity up to this point A? There will be surely work done because your Q1 need to be brought against the external field. So that is the first part. Got it? Where when you, if you want to find potential energy and work done are almost same. That much amount of work done in bringing will be stored in the form of potential energy, right? So your work done will be the sum of the work done in bringing Q1 and in bringing Q2. Got it? This is due to the amount of work done in bringing Q1 from infinity up to this position A. That means at this point there will be potential, electric potential due to this electric field, right? That potential is denoted by this portion. Got it? So potential times Q will be equal to simply your work done. Why? Because we define what your electric potential is defined as work done per unit charge, right? Work done per unit charge. So what happened? Work done will be V into Q. Got it? That, or Q into V you can say. So Q1 times V. What is V? Electric potential at that point due to this external field. Similarly, when you try to bring Q2 from infinity up to this location B or position vector R2, there will be what electric potential due to this electric field at the position B or position vector R2. That part is denoted by this. What is this? V R2. This doesn't mean that V times R2, okay? It doesn't mean. It is V at the position R2, we can say. Got it? Electric potential at the position or at the point having position vector R2, you can say in that way. So electric potential times the charge Q2. What is this? VR2. This VR2 is the electric potential due to this external field at this point. Got it? At this point B, that is denoted by this VR2. So VR2 times the charge Q2, that will give you the amount of work done in bringing Q2 against the external field. And this part is what part? This part is nothing. This part is the amount of work done in bringing Q2 against the field due to Q1 here. Q1 was already residing here. So this Q2 need to do two work. One in bringing against that external field E. Another part is what? Against the electric field due to what? Q1. Q1 will be also giving electric field. So against that electric field, your Q2 need to do an external additional work, okay? So an extra additional work, that extra additional work is this one. So what is this then? Q1 divided by 1 by 4 pi epsilon naught times of R12. This is nothing but this is the potential, electric potential due to Q1 at the point B. Got it? Electric potential. This was electric potential due to the external field at the point B, and this portion is the electric potential due to Q1 at B. Got it? So this is the total. If you want to find out the total work done, you need to add it up all these work done, okay, and then you will get it what is known as what total potential energy of the system of charges when you bring that system of 2-point charges inside an external field. Got it? Yes, let's wind up here, and we will try to do in the next class as what electric potential energy, okay, of an electric dipole when placed inside an external field. Okay, we will do that one later on. Let's wind up. Okay, thank you.